Fulbright and Belgian American Educational Foundation fellow, postdoctoral fellow at Penn State University. But what I will do today is mainly summarize my PhD research work, which I completed and defended in November past year at the Vrije Universiteit Brussels in Belgium. And I will do that mainly to show how that storyline leads to the work we're doing right here at Penn State with Christelle Vautier at the end of the talk, because it's all still fresh and under development, of course. So a 4D perspective on magma-induced deformation of the Earth's upper crust in nature and laboratory experiments. That's what we are going to look at today. So I think we're all pretty familiar with this image. This is the 2018 Southeastern Rift Zone eruption at Kilauea on Hawaii. And this is what happens when magma reaches the surface, right? We can all observe it. Lava flows out of a vent here, forms a lava flow, threatens some personal property. Luckily enough, in this case, not too much life. And one of the major aims, or maybe even the major aim of volcanology, our science, should be to try and understand the processes that lead to this event, what's happening below the surface, below the ground, before that magma reaches the surface, with the final aim, of course, to hopefully better forecast these eruptions and mitigate the effects on personal property and, more importantly, life. And one way of understanding these subsurface processes is to look at geological outcrops. Here's an example of a dike, this vertical feature here, piercing through a stack of breccias and lava flows on Moeli Island, one of the Comoros Islands, to the northwest of Madagascar. And these geological outcrops can teach us a lot, especially if we throw every possible up-to-date, state-of-the-art modern technique at it, but they can only go that far because they represent the final result of a magma intrusion. And we still need to make inferences about the processes that led to this structure right here. So in order to really understand the dynamics of the magma intrusion process, we rather like to go back to active volcanoes, right? And here is an example, the 2014 intrusion on Iceland, the Bardarbunga holochron intrusion and eruption. And we have several techniques at hand to understand the dynamics of the magma intrusion process. One of those is looking at surface displacements. As magma makes its way through the subsurface, it's going to create space for itself, deform the host rock, and that's ultimately going to lead to displacement at the surface. And what you see here on the top is a interferogram that yields from interferometry using radar satellite images. And the fringes, those colorful fringes you see there, represent surface displacement in the line of sight of the satellite. We can use INSAR for that. We can also use GPS stations on the ground to get continuous measurements of that surface deformation. So surface displacement is one, but as magma moves through the subsurface, it might also fracture the host rock and so induce seismicity. And those earthquakes can be, again, measured, located, and might give us an independent indication of where the magma is at a certain point. And even in some cases, the earthquake mechanisms that are linked to that. And combining both, even with gravimetry as well, we can come up with some models of how the magma intrusion looks like. And we have analytical and numerical models for that to invert our observed data and get an idea of magma intrusion geometry, orientation, volume, overpressure, etc. The thing is, with these models come a range of assumptions we make because we can still not observe the magma moving below the ground directly. And one of the major assumptions here is how exactly the magma intrusion front propagates through the host rock and deforms that host rock. Is that either using mode 1 fracturing, of which you see a sketch here, so by opening mode fracturing and elastic deformation of the host rock, and the result we would expect then would be a tapering, pointy tip you see here. And I'd like to point out as well that tip cavity there, which basically exists in the model because the viscous magma can't fill that narrow space at the fracture tip really. Or is it maybe contrastingly through a theory called viscous indenters, where the viscous magma, as it were, bulldozes the host rock ahead of it and creates a plastic deformation, creates shear mode fracturing in that process zone around the intrusion tip. Or maybe a combination of those. And here is an image of Spakapan et al. 2017, which summarizes a range of propagation models being proposed in between those two end members, where fluidization, ductile deformation is also taken into account. And the question really remains, which of those models really is the dominant one, or in which circumstances one would dominate over the other and would become more important. And that question was what my PhD was all about. And we attacked the question using two different ways. We first went into the field and then executed laboratory experiments, developing a new technique for that. And I'm first very shortly going to take you into the field. This is a study we did on Hovadøya Island, of which you see a location there on the top left of your screen. It's a small island in the Oslo fjord, just in front of downtown Oslo, which you see in the background, in this Google Earth image. And the outcrop, of which you see a drone image on the bottom there, is basically a horizontal glacially eroded surface, so a 2D outcrop. And there we studied the structural interactions between the host rock beds, which are going top down on your screen right now, and some thin dike intrusions or dikelets, which intrude there. And I will soon show you some zoomed in images. And I'll do this quickly for sake of time, but you can read all the details in our GQ paper, which we published earlier this year. And we did several things. First of all, we took drone images and close range photographs with a handheld camera and produced orthorectified images. And on those images, we mapped and measured the orientations of the dikelets, of the fractures in the host rock, and of the bedding planes. And what we saw was that overall the dikelets, which are red here, have orientations similar, parallel to the fracture network in the surrounding host rock, which is dominantly north 150 degrees east with a secondary north-south orientation. And then the bedding planes are roughly perpendicular to those fractures and dikelets. And there's a normal fault running through the outcrop as well, which has an azimuth parallel to the bedding planes. And if we zoom in this outcrop, there's over 60 dikelet tips present, so we can really have a good view on that process zone ahead of magmatic intrusions here. And that's why we went there. And I should mention that the host rock is overall a carbonate bearing mudstones and shales. And most of these tips, if looking at the geometry, were pointy taper tips, which corresponds to that mode 1 opening mode geometry we would expect. So either these were single pointy tips, as you see on the top left, or where we had overlapping taper tips. They were mostly asymmetric due to the overlap with some bending of the layers in between. And then we had 11 blunt tips as well, which were much more similar to viscous indenters, as you would expect, with lots of dense, brittle fracturing around them. And if we look at some more of the deformation in the surrounding host rock, we see that those diclets mostly followed those pre-existing fracture networks. As you see on the left here, a very nice example. Or bent the host rock in between overlapping tips, sometimes with normal shear displacement along some of the broken up beds. And there's, again, much more detail in the paper, but if we zoom in on the diclets themselves, there was a very peculiar feature there. The dicores themselves were dark, but the edges and these pointy, narrow dike tips or cavities even were filled up with a whitish material. And throughout the outcrop, we also found white calcite crystals. So I really wanted to understand what the role was of that whitish material on the edge. Is that just a chill margin, or what's really going on? That material was able to fill up the narrow cavity space that the dicore couldn't reach. And for that, we ran micro-XRF, elemental maps, line scans, as well as carbon and oxygen stable isotope compositions. And again, further detail in the paper, but overall, we came up with an understanding that most of the magma here must have propagated along those pre-existing fractures in a mode 1 opening mode fashion, creating those tip cavities ahead, and some other tips must have intruded in a mode 2 fashion, creating shear mode fractures. So we have a dominant opening mode propagation with some subordinate shear mode propagation. All the while, the hot magma must have interacted with the carbonate-bearing cold host rock, and it is known that this contact might result in dissociation of the carbonate into CO2 gas and calcium. And from our elemental maps, we saw that probably that calcium migrated into the magma along with pore water, decreasing the viscosity of the magma along its edges, allowing it to intrude into the narrow space, plus some CO2 gas that might have accumulated ahead of those tips. And then this lower viscosity mixture of pore water, magma, and CO2 gas might have assisted in the opening of the fractures ahead of the magma. And then when all of this system was solidified, cooled down enough, hydrothermal fluids might have circulated and deposited calcium crystals in the remaining voids. So this is a really nice example of a dominant opening mode, but as well as shear mode propagation happening simultaneously in one location, one quite constrained location. And to understand more about this propagation, we went back to the lab, as that is my core business, let's say. And when people have experimented, have simulated magma intrusion in the lab, there's really two ways of going at it. Either you do assume that host rock, the Earth's crust, will deform dominantly elastically, and use gelatin, which you see an image of here on the left. Gelatin is elastic, but can rupture due to a fluid injection, and its great advantage is that it's transparent. So you can observe the intrusion as it develops below the surface. But if you're not happy modeling the Earth's crust as purely elastic, then there's granular materials, like here an example from Olivier Galland, silica flour. And when we inject a liquid magma analog in there, we can observe the surface of the experiment using 4 cameras in this case, and get the surface displacement out of that. In the gelatin, I should note, this is a polarized image where you can actually observe the stress field induced by that red injection of dyed water in the gelatin. So these experiments have led to a much better understanding of magma intrusion processes, the dynamics of that. But the main issue when I started my PhD, I found was that we still lack a proper 3D quantification of those magma intrusions, but as well the deformation induced by the analog intrusions in the material around it. And a time understanding, an understanding of the development, growth of the intrusions over time, as well as how the magma-induced strain field develops. And for that, we developed a new technique in my PhD using medical X-ray CT. But before setting further on that pen, we had a little issue. Because in the lab in Brussels at the VUB, we traditionally used granular mixtures of sand and plaster in the experiments. And we got wondering, do we really understand the rheology, the behavior, the mechanical behavior of such mixtures? And it turned out no. So we did a range of tests, material tests, and this is a paper in preparation to submit to Technophysics as soon as possible, I hope. The current stay-at-home situation has set everyone's work back a bit, I guess. But what we did, first of all, is run ring shear tests. In a ring shear test, you deposit the material in an annular cell. You place a lid on the top, load the lid, and then rotate the sample. And the lid itself is connected to stress sensors, which allow you to measure the shear stress during that rotation. And so get an idea of the mechanical behavior of the strain behavior of the material. And for pure sand, the shear stress curves, shear strength curves are quite known. You see here an example for pure sand. On the horizontal axis, you got shear displacement of the sample, and on the vertical axis, you got the measured shear stress. And those different curves represent increasing normal loads which are placed on top of the experiment. And it was well known for pure sand that as you start deforming the sand, you will very quickly increase the shear stress to a peak at failure of the material, where you localize a shear plane and then decrease to a kind of stable strength. But as we ran a series of mixtures going from 0 over 5 to 10, 20, 35, 50, 70, and 100 weight percent of plaster, we started noticing that as the normal load increased and the plaster content increased, that initial peak disappeared. And this is more typical for ductile behavior of materials. So basically what we saw in our sand plaster materials is as you increase that normal load and plaster content, we move from a brittle into a ductile regime, which is actually pretty similar to how we understand the Earth's crust behaves as well as we go deeper and deeper into the crust, and so analog in our sandbox. So really a pretty complex behavior. And we then ran, because those ring shear tests are pretty poor at constraining the cohesion of granular materials accurately enough, we ran a series of direct shear tests and tensile tests to constrain the failure envelope of each of our materials. I showed 3 examples here. We basically constrain that normal stress on the horizontal axis versus shear stress space for our materials, and then applied a simple linear Coulomb criterion and a combined curved Griffith-Moore-Coulomb criterion, which is red in the bottom diagrams, to try and constrain the cohesion of the materials, which is the intercept of these regression curves or interpolation curves with the vertical shear stress axis. And again, without further detail, what we basically found is if you look at cohesion and friction coefficient on your right, cohesion on your left, we see that as we increase the plaster content in the material, we do overall increase their strength, but at about a 35% weight percent plaster content cutoff, we move into a more complex behavior where the curved Griffith-Moore-Coulomb criterion much better describes the material than a linear Coulomb one. So as we add more and more plaster to those sand plaster mixtures, we move into more complex behavior of the material. And that was really important for us to understand how our experiments would behave. So once that was done, and those few slides took over half of my PhD, a lot of work went into all the different tests, we could finally move to the experiments themselves. And here's a picture of our new 4D laboratory monitoring method. This is a sandbox, 20 by 20 centimeters, connected to a syringe filled with golden syrup, which is the magma analog, in a medical CT scanner. What we did is basically pump golden syrup, our beautiful, and everyone knows it probably, Tate and Lyle's golden syrup, magma analog. We pumped that into the sandbox and then scanned continuously. And we could do that using a wide beam X-ray CT scanner at the University Hospital in Brussels. And why specifically that scanner? Because standard CT scanners have only a sensor of 4 to 8 centimeters wide, so they wouldn't be wide enough to scan our box continuously. But these wide beam CT scanners, which you find mainly at the ER rooms of hospitals, are made for scanning a patient's head. So they have a simultaneously, and they have a 16 centimeter sensor, which allowed us to capture most of our box. So the box is in there, we inject golden syrup, and then take a scan every 20 seconds, and the acquisition of one single scan would take 1 second or less. So in that way, we could gather a whole time series of 3D CT images during injection of our analog magma and get an idea of really what happened below the surface during that intrusion process. And I should mention this work is published in Frontiers in 2019 as well. And here is an example video of a cryptodome intrusion in a low strength mixture. You see at the bottom left panel, the rendered 3D intrusion growing as a single blob, and then a finger develops that injects into a ring fault that then proceeds to erupt at the surface. And these videos are online as well at the Frontiers publication if you want to continue looking at them. And what we can do as well is extract the surface displacement from the CT scans. And we see how with this type of experiments, we get a quite dome-shaped symmetrical uplift that then evolves into asymmetry and finally extrusion of the syrup. So the nice thing about the CT scans, and here, if you got it, you can use your 3D glasses, hopefully. The nice thing is we can render the geometry, the 3D geometry of the subsurface intrusion. And here you see some time steps of that low strength, that intrusion into low strength material, where you indeed see that, that fat blob of golden syrup from which then a finger extruded towards the surface. And if we do the same in a medium strength material, about 120 Pascal, we get a completely different geometry of the intrusion. Basically, you get, again, that dome-shaped uplift. But if we render the intrusion, it is gonna come. Yeah, there we go. No, let's go one back. Sorry for that. This is a lot of data, and so PowerPoint takes it a bit slow sometimes. Let's see. Can we go back? There you go. This is a cone sheet rather than a cryptodome. And if you rotate it, hopefully you can see really the 3D geometry here of an inverted cone. Notice also how it has several splays towards the surface, and that small protrusion you see there on the top rotating by right now, that is the point that eventually led the finger that eventually led to extrusion at the surface. So even though we get a minor crack opening, a minor fissure opening at the surface, you got a whole 3D complex 3D geometry below the surface, which we can follow up using the CT time series. And if we then finally go to high strength material, about 360 Pascal, we see again something completely different. We get a singular crack opening towards and moving that syrup towards the surface. If you look at the surface displacement, then it's much more symmetrical, much less pervasive, several cracks open, and finally one will act as the eruptive fissure, if you like. And if we again render that intrusion, then remember that 2D vertical slice, it showed a quite simple thin line going towards the surface, but in 3D, that intrusion is quite complex. It's not a simple rectangular plane we imagine as dikes should be, but a complex 3D shape that shifts orientation as it moves towards the surface. And finally, again, quite centrally above that inlet leads to extrusion at the surface. So if you look at those geometries, they are quite complex indeed in our experiments. And this is an image I received from Alan Bischoff, looking at the volcanic plumbing system below a buried Miocene volcano offshore New Zealand. And this rendering has been produced from seismic reflection data. And indeed, we see quite complex intrusion shapes popping up there as well. And if you take a look at the cone sheet example there on the left from Alan, then that definitely reminds our cone sheet intrusion I showed you just earlier from our experiments. So our experiments really allow to understand better the process that leads to the production of such geometries and the structural deformation in the overburden, the way faults propagate through that, as these geometries, these intrusions are formed. So there is the qualitative value, if you want, of those CT, of that CT method, but these are just nice images, right? We wanted to quantify things. And for that, we use digital volume correlation. It's basically a variant of digital image correlation in 3D, where the algorithm takes a 3D CT scan at time 0, subdivides it into subunits of voxels, which are 3D pixels, and then tracks those groups of voxels through time using their wide gray or grayscale texture. And that way we can calculate a full 3D displacement field, a vector field basically, from which we can derive several strain components in 3D again. And I'm showing here on the left that low strength cryptodome example and that high strength dike example. And I'm just showing a vertical slice through the displacement and strain, maximum shear strain fields. We have vertical, horizontal strain components as well, of course. And the colors represent the maximum shear strain. The black arrows represent the displacements we calculated. And basically what we see is that in those low strength materials, it is shear mode fracturing and shear mode, shear mode displacement in our models, while in the higher strength materials, it's rather opening mode deformation that dominates, but there is still shear mode deformation present. Very similar to what we saw in that Oslo case, actually. So, so we now have a nice grasp, I hope, of what happens in those experiments if we use granular non-elastic materials as our analog host. And in the last part of my PhD, we took that back into the field. And this is stuff that has not been published yet because we're still working on that, as it leads to what I'm doing here at Penn State. Here is an example of an interferogram collected during an eruption at Piton-la-Fournaise volcano earlier this year, January 2020, from the volcano observatory of Piton-la-Fournaise. And Piton-la-Fournaise is really a very active volcano with, I think 2019 had 5 eruptions, 2018 4 at least. And some of these displacement fields measured there are quite complex, but can incite some thoughts as well. And here are 3 examples from 2018 eruptions provided by Nicole Richter. And what you see on the top are unwrapped interferograms, where red represents inflation, uplift, and blue colors represent deflation or subsidence. And at the profiles at the bottom, and these still need to be cleaned up, these are not the final results, but these profiles are located, by the way, along the white dotted lines on the interferograms. What we see is that in one case, the August to November event, we only get uplift above that intrusion, while in the other 2 cases, we get mainly dominantly uplift, but some subsidence on the opposite flank of the eruptive fissure. And let's compare that now to results from our experiments. What you see here are profiles extracted just below the surface in our sandbox from the displacement fields we calculated using digital volume correlation in the CT scans. And on the left side, we have our subvertical dike, which you saw a video from before, where blue is time step 1, yellow is the final time step. And you see how that surface displacement or near surface displacement evolves from an asymmetric uplift to a two-bulged uplift with a central trough, which by the way, barely shows any subsidence because that central negative displacement is within the error margins of our technique at this moment. And on the right, you see an inclined sheet, a steeply inclined sheet, which produced a asymmetric uplift again with the largest uplift along the hanging wall, above the hanging wall of that inclined sheet. And this made us thinking further because if you look at other analog experiments, even gelatin experiments don't show much subsidence above a dike, whereas in simple elastic dislocation models, it is assumed, theorized if you want, that above a vertical dislocation in an elastic medium, you get that two-bulged uplift above the flanks with the central subsidence above the dike apex. And as we tilt that dislocation, we move into an asymmetry with a single uplift above the hanging wall, subsidence on the other flank of the intrusion. And if we move to a sill or horizontal sill, we just get simple uplift. But at Pitol-la-Fournaise, it is often difficult to explain a sill being intruded and still leading to a to eruption 2 kilometers higher. How does the magma get from that sill, that horizontal sill, all the way up to the surface? It's difficult to explain sometimes. And part of that might be due because we apply elastic models, assume elastic rheology for volcanoes that are often as weak and loose as Piton-la-Fournaise, for example, where when a magma intrusion propagates towards the surface, we sometimes barely see any seismicity guided by that. So maybe shear mode deformation in such cases is much more prevalent than previously thought. Now, I realize all of these past sentences are inferences from our part as well. So we thought, well, how can we further understand how applicable the elastic dislocation models are to cases, to what we think are sometimes brittle, shallow systems? Well, why not try to apply the elastic dislocation models to our experiments? And that's what I'm doing right here at Penn State with Christelle Gauthier in a project called Lab Volcano Geodesy. So we have surface displacement maps of several of actually all of the X-ray CT experiments, as well as some others we just run in the lab using photogrammetry. Where we got at up to this point is an example here of a forward model where we place an Okada dislocation. So that's a rectangular opening mode dislocation at depth below a horizontal surface, because our sandboxes as well don't have any topography, so we don't bother with that at this point. And on the left, you see a vertical displacement map from that inclined sheet experiment I showed before. In the center, the model output, and then on the right, the residuals we calculated. And this is just a forward model, so it's of course not near what potentially could be the best fit, but it gives a starting indication of in which parameter space we'll be looking, where we see that some of the parameters seem to fit quite well in the model to what we see in our experiments, the dip of the dislocation, even the strike, but to jump out at this moment, which is the length, which in the model needs to be much smaller than what we know our intrusion is from the CT experiments at depth, and the opening, which we put here at 1 meter in the model to obtain similar magnitudes of displacement as seen in the experiments. Well, actually, if you would scale that up using our length scale of our experiments, we would actually be modeling a dike of 114 meters in thickness, which I hope most of you agree is probably quite unrealistic. So we're right now working on inputting this data into inversions and soon running an inversion model on this to get a blind idea of the best fit model parameters that would come out of inversion models, and then compare that to how we know our magma intrusion, analog magma intrusion actually looks like from the X-ray CT scans. This is of course a most simple model possible, and in the future it will be possible to move into more complex dislocation geometries, discretizing it using boundary elements, etc. But this is where we got right now. And what I forgot to note is that in the observed map there, you get vertical displacement. This is an extract near the surface from that digital volume correlation data, so from our 3D strain field, which means we also have the north-south and east-west components, which we will take along in the inversions later on. So that was just a quick overview of the work we've did in the past few years. and that is definitely still ongoing. So in conclusion, we found in our Oslo field case, complex deformation mixed between dominant opening mode and secondary shear mode deformation. Host rock heterogeneities, existing fractures clearly have affected the pathways the magma took, and thermochemical interactions between the magma and the host rock, the carbon-bearing host rock, might have played a role in that propagation process. Using sand and plaster materials, we now have a much better grasp of their complex mechanical behavior. And because of the quantification process, we can now use that material strength really as an experimental variable. And varying that strength, we see that at low strength, we get cryptodomes to cone sheet intrusion geometries, and mainly shear mode deformation, while at higher strengths of our materials, we rather get dikes that propagate dominantly through opening mode, but as well with secondary shear mode deformation of that granular material. And using our experimental results, we hope we might propose alternative interpretations to deformation patterns seen at volcanoes now. The question, is it a sill, is it a dike, is something we are now able to look at and will continue to look at into the future. And then furthermore, to close up, this work will continue. I am actually leaving next week back to Europe and starting a postdoc at ULB with Karen Fontaine, where we will rerun some of the experiments using the X-ray CT, but then applying a far-field extensional tectonic stress, if you want, to our sandboxes to investigate what the influence is of that extensional stress regime on the surface displacement. Do we get more subsidence above the dike, etc.? And the interaction between the extensional strain field and the magma-induced strain fields. And with that, I close the scientific part, but I just want to mention that YAFSE ECRNet, of which I'm part, we hold monthly almost virtual panels, and we started posting some of the recordings of the events on YouTube. So go and check out our YouTube channel. We had another event past week, and we'll be posting the videos as soon as we get them chopped up in manageable pieces. So thanks. I'm here for questions.
Thank you, Sam. That was excellent. I'll open this up to questions. I think I see a question in chat already. This is from Leif Karlstrom. And Leif says, congratulates you on the experiments. And he writes, is the scanning resolution sufficient to image evolving intrusion tip geometry? And he follows, are there systematic variations in tip shape as a function of host material strength that could inform your field observations?
Yeah, so the problem with the medical CT is that the resolution is quite coarse. It's an ongoing balance between, so if you want the time resolution, if you want that temporal resolution, you can't get the high spatial resolution. So at this moment, those medical CT scans stand at 625 micron, so micrometer per voxel. And you obviously need several voxels to image that geometry. So it's difficult to really zoom in at the tip geometry itself and then get a good idea of the strain field very locally. Our current strain fields give rather a broad overview, if you want, of the entire displacement and strain fields. Yeah, that's just the way it is. Either time or space. You have to make a choice. Yeah.
Other questions out there? Pedro writes, I would like to ask you about software you use for CT imaging processing.
So as a first step, it's the CT software that comes with the machine. So the videos you see of the rendered intrusion surfaces, that's all inherent to the CT scanner itself. And then afterwards, I use medical software. It's a 3D slicer, it's called, which allows to render those intrusions. And then for calculating the digital volume correlation stuff, the displacement and strain fields, it's the LaVision software, Strain Master, which is a paid software. But I'm dying to test out a newer open source Python code called TomoWarp 2D, which is available from the University of Oslo, and that would allow to basically do the same calculations. Yeah, so that's a bit what I use at this moment.
And it looks like there are more questions actually. And Maurizio writes, I love the integration between lab. Okay, he's congratulating you on the integration of lab, fieldwork, and modeling. And as other questions come up, please go ahead and use the raise hand function. I can unmute you. That's fine too. I guess I had one question, Sam, and that is, do you ever notice, maybe through dissecting your experiments, do you ever notice any residual microscale granular sorting of your mixtures after a propagation event?
After a propagation event, well, I'm not sure about that. I haven't really looked into that, because if just in the lab, then we freeze the experiment. So then you just throw out the sand and plaster to look at the 3D geometry of the plaster. And then in the CT scans themselves, maybe we'll be able to see it, but I haven't paid much attention to that. We actually, I try my very best to make the pack as homogeneous as possible. So we mix it, pour it into the box, and then compact it as quickly as possible using a shaking table, but like only a few seconds. So there can't be any segregation of grains. So I haven't really seen that. At least it's not that obvious then.
Right. I guess I have a kind of related question to the Leaf's question, which is, do you see dilation in front of the crack? Can you resolve the dilation of the granular mixture?
Yeah. You actually, in some of the videos, you can see even in the CT videos, you can see a compaction wave propagate through, and in the strains themselves as well. Yeah. You see that. You see compression, dilation, definitely happening. Yeah.
They're very neat experiments.
Yeah.
Other questions out there? Well, let's see. Actually, there may be some questions here in the chat. Okay, this is a question from Brenna. How does the viscosity of the golden syrup compare to real world magma viscosities? So I think, what's the scaling you're using, I think?
Yeah, so the viscosity of the golden syrup is highly temperature dependent. Let's start with that, especially around room temperature, which is awesome. We've constrained that at the CT scanner, air-conditioned room, it's about 50 Pascal seconds. And it would scale up to some medium viscosity magma. So not your low viscosity basalt, but definitely as well not your high viscosity rhyolite. Falls somewhere in the middle.
We have several other questions on chat, I see. Okay,
yeah,
so
shoot.
Writes, in your rheological measurements in the Schultz ring, did you vary the confining pressure as well as the shear stress?
Yeah, so we varied the normal load, so the confining pressure, if you want. We varied that. We did not vary the shear stress, which you would vary by varying the rotation speed. We did one test on one of the materials to just have a check if there's a wide if there's big variation as you change those speeds, but within the range we were looking at, not really. So we didn't look further into that. No.
Larry Maston writes that 32 years ago for his PhD, he studied the surface displacements above a shallow dike in a box containing a mixture of flour and sugar. The region above the dike top began to subside to form a graben once the first cracks formed at the surface. But before those first cracks formed, there was no obvious subsidence. Did you notice a similar sequence in your experiments?
So, yeah, with that difference that we don't get this, we don't get this this pervasive subsidence at the surface above the dike tip, and Olivier Galland has talked a lot about that as well, that doesn't happen in their experiments. So Larry, if I remember correctly, your experiments used a sequence of metal plates intruded in a sheet, into a sleeve, sorry. So you were wondering at some point if that consecutive intrusion of one plate next to the other might force that subsidence rather, compared to using the injection of a fluid. But I hope to get a better understanding of that exactly by applying that far field extensional stress. Do we then pick up that subsidence above the dike, yes or no? So in other words, would that subsidence above a dike be linked to the fact that most of our examples are in extensional, either tectonic stress field or volcanic rift zones? That is something we don't really understand properly at this point, I think.
Yeah, it looked like your configuration was a little bit different from mine in that you had you didn't actually have a dike at the bottom. You had sort of it was more of a circular intrusion, right? You were intruding. Yeah.
Yeah, of course, it quite rapidly evolves into a planar sheet. But indeed, it's more similar to the gelatin experiments in that sense. It's just a more complex penny-shaped crack, if you want, that we form.
Right.
Yeah. So does that have something to do with it? I don't know. We hope to try lateral intrusions as well to get a better understanding if that makes a difference. Yeah, it's an interesting question.
Thank you.
No, thank you.
And a question from Jake Jordan. Have you thought about making some estimates for compaction-induced permeability changes?
We haven't done that yet, but we had a student look at increasing the depth in the box, so the height of the sand pile above the inlet, if you want, and she found some interesting pointers towards the influence of compaction in the experiments. So it's also something we would like to look more at. What I did do in the sand plaster characterization is do an estimate of porosity, porosities for the different mixtures, and we think much of the behavior we see across those different mixtures is linked to a drastic change in porosity as we add more and more plaster to the mixture. But that has been a theoretical estimate of porosity, not direct measurements. And then exactly in the experiments themselves, as they go on, we haven't looked at syn intrusion, at quantifying syn intrusion compaction. That could be something great to do as well. There's still a lot. Yeah.
Thank you. Are there other questions out there? Hopefully I didn't miss any of the questions in the chat. I tried to catch them all. Sam, there's a lot of other great, congratulatory comments too here in the chat. That I'll let you also take a look at. I think the recording will copy that too. Other questions, feel free to put it in the chat, or you can just ask the question if you just raise your hand and unmute yourself. Well, great. Well, why don't we had a lot of great discussion. It's a good point to stop, I think. One thing that we can continue is a discussion on the Slack channel. And if you don't have a link to that, please just let myself or Ben know about it. And other than that, thanks again, Sam. That was a great talk and great discussion. And please join us next week for Hannah's talk.
Yeah, thanks all for tuning in. Bye all.
I usually leave this open for a few minutes here in case people want to last minute questions or discussion with a smaller group. Well, that was fantastic, Sam. I'm really excited to hear about your extensional work coming up here.
Yeah, I'm excited as well. It's just been a tough time.
Yeah, logistically, yeah. I can imagine this is very challenging.
We're moving next week back, so and we know since past week. So it's been to hell and back again. We'll be happy to just be home and finally focus on life instead of all this. Yeah. State Department is basically evacuating Fulbright grantees.
Oh, really? Oh, yeah. Wow.
I guess they have something like all the internationals get lost, get out. We don't want to deal with you. It's something like that. Yeah.
Oh my. So they transport and all that sort of thing.
Yeah. They put in a charter and bring everybody home.
That's good.
Yeah. So.
Well, good luck getting back to some semblance of normalcy, I guess. And
the new postdoc is great, and we can perfectly continue all of the stuff I started with Crystal, get the new experiments running. So a lot of the questions raised today are plans for the near future, definitely.
Yeah, those are very nice experiments you showed. Thank you. It was a great presentation.
There's still a lot of work to do on the visuals, but well.
No, the X-ray CT data is amazing to be able to see these things in 3D and see your visuals in general were very nice.
Yeah, it's one of the main reasons for going back to Brussels. I can access the same scanner again in the postdoc, and that's awesome. Yeah.
Have you thought about adding in some additional material? I mean, the problem with experiments, as you know, is you can very rapidly have an infinitely large parameter space. So you want to avoid that.
It goes boom.
Yeah, exactly. But having